Hello, this is Math 280 Multivariable Calculus. I'm Professor Wheatley. Today's topic is going to be polar coordinates and multiple integrals. Okay, so we talked a lot about doing double integrals in rectangular coordinates when we have rectangular regions, and we saw even with non-rectangular regions we could look at things in terms of type 1 and type 2 regions and do it that way. But certain regions, in particular circular ones, well, they may be more easily described in polar coordinates, or more easily, let's try to spell describe correctly, more easily described in polar coordinates. And we're going to see that this may make our lives actually a whole lot easier when we try to integrate, because it's going to make our limits easier and our functions easier to deal with. Okay, so there is a minor tweak, though, and it bears out some theoretical understanding of what's going on. So first things first, let's recall what a polar coordinate is. So you have a point xy in rectangular coordinates. And it becomes a point r theta, right, in polar coordinates. So it becomes a point r theta in polar coordinates with the following relationships holding true. So x is r cosine theta, y is r sine theta, and r squared is x squared plus y squared. And the picture that goes along with this is this standard picture where you have a point xy, there's xy, there's your y term, there's your x term, the r term from the Pythagorean theorem, all right? And there's your theta. And so we see here that cosine theta is x over r. That leads us to this. Sine theta is y over r. That leads us here. And r squared by Pythagorean theorem is x squared plus y squared. Right? So that's what polar coordinates is. Okay, so when we integrated in rectangular coordinates, integrate in rectangular coordinates, you broke up a region, what am I calling it, R here, into rectangles. All right, so you broke things down into rectangles, and you made columns, and you took volume, and all this other good stuff. Well, the same thing is basically going on here, only we're not breaking things down into rectangles because we have circular regions, all right? That's the idea. So when we integrate in polar coordinates, we break integration, breaks, I guess, breaks up a region R into polar rectangles, right? Polar rectangles. All right, so what's a polar rectangle? Let's draw one. So let's see here. So we have two angles, say theta equals alpha, theta equals beta. Right, so let's make this multimedia here. So there's beta, there's alpha, right? So there's our two angles, right? And we also have two radii values of circles. Right, so we'll call this, well, I guess, so we'll call this r equals a and r equals b. So those are radii of circles, right? So pieces of radii of circles. And then this region in here, all right, so everything in here, I've actually drawn over my r equals b, but there it is. This is your region R. That is what a typical polar rectangle looks like. So this is a polar rectangle R, right? The points are in polar coordinates, so we want them to be r comma theta, right? Well, our theta or our r values lie between a and b, and our theta values lie between alpha and beta. Right? So there's a polar rectangle. The r values lie between a and b. The theta values lie between beta and alpha. Okay? All right, so there's a polar rectangle. Well, this is our region R to integrate over, maybe. So now the question is, what do we do? Well, just like with rectangular coordinates, we broke things down into smaller rectangles, and we did that over and over and over again, took a limit. Same idea here. We're going to break down the big polar rectangle into smaller polar rectangles and take a limit of areas. Okay? So let's draw the corresponding picture over here. So there's our angles again. All right? There's our polar rectangle. And we'll break it down into smaller pieces, just like we did with regular rectangles, right? Maybe we ought to have an extra line there. There we go. Okay? So we're going to break this thing up, right? So we can then subdivide R into polar subrectangles. All right? And so, I don't know. Let's take a typical one, say that guy right there. And we're going to number these guys, and numbering doesn't make a difference how we number them. We're going to call it R of k. That guy has area AK, and he has coordinates little rk, little theta k, right? So there's a typical polar subrectangle with area AK and coordinates rk and theta k, okay? And so we can form a Riemann sum, so we'll have this sum. So let k equals 1 to n. So, you know, how many of these are there? Well, maybe there's 20, maybe there's 30, maybe there's 40, maybe there's more and more and more, right? And our function is defined in terms of polar coordinates, so it's some function f of rk theta sub k. And the change in the area, right? Summation, right? So this looks just like the function of f of x comma y we did in the last section with rectangular coordinates, only this time we have polar coordinates and polar rectangles as opposed to regular rectangles, but it's the same idea. So you're just going to make n go to infinity and take a limit. Right? So you make n, you know, you take more and more and more of these. They get smaller and smaller and smaller, better and better approximations of what's happening. Right? And you get the limit as n goes to infinity of Sn is the double integral over the region R of f of r theta dA. Right? So double integral over the region R of f of r theta. So what this is all saying is that the integration, at least at this point, looks exactly the same as double integration over rectangular regions, only we've changed to polar coordinates. Now, here's where the big difference is, though. So, okay. The question is, we need to figure out what the area of each of these polar subrectangles is and look at the change in it, right? Okay, so what we need the area of a typical polar subrectangle, A sub k. Well, we don't want it, actually we want the change in area. So, because we started off with delta A sub k down here. We want delta A sub k in terms of the change in the radius and the change in theta, right? In other words, our function depends on r and theta. What is our area? Well, so we want our area to depend on r and theta as well, okay? And so we'll start, so a wedge-shaped sector of a circle, right? So think about this as, this is some circle radius up here, right? We have this wedge-shaped sector of it, right? So if our circle has radius r and central angle theta, well, then what is the area of this wedge-shaped sector? So area of wedge, well, the area of a circle, area of wedge equals, don't know, but area of a circle is pi r squared, right? And the wedge is some part of the circle, right? In particular, the circle has 2 pi radians to it. The wedge is some theta fraction of it, right? So let's see here. So times the fraction of the circle the wedge is representing, right? Which is however much theta is. So if it's half the circle, for example, so it would be pi over 2 pi, so it would be 1/2 or something like that, So whatever this fraction of the circle is, right? So you multiply that out, the pi's cancel, and you get 1/2 r squared theta. So this is the area of a circular wedge, okay? And that's helpful to us because, what are these things? These are wedge-shaped objects here. That'll help us out a lot. Okay, so now let me redraw this picture over here, only I want to zoom in on that single polar subrectangle. So I want to zoom in on that single polar subrectangle this time. Okay, so let's see if we can't be pretty precise here. So, all right. There's a couple angles. There's that. Get that out of there. Okay. So we're going to zoom in on a single polar subrectangle, RK. Okay. All right, so here's a single polar subrectangle. And in fact, let me put the center of it right there. So that's, say, little r sub k, the center of it. All right, well, this thing is going from one angle to another, right? So there's an angle over here and an angle over here. So this top piece is delta theta, right? The change in the angular measure. Going from one angle to another, that's the change in the angular measure, right? And we're going from one radius to another, so that's the change in the r measure, right? Okay. All right, now, the question is, what is this r measure down here, and what is this r measure down here? Well, maybe we can draw a line here and show what's happening. So, not too terrible. All right. So there's the radius r sub k right there, right? So this is the radius to this point, to the center of the polar subrectangle. Okay. Well, if this is the center, then this is half of delta r down here, and so is this, right? So delta r is chopped in half, and half of it's down here, and half of it's up here, right? So what is this point? Well, if that's r sub k there, this is r sub k minus delta r over 2, right? It's r sub k minus half delta r. And this point up here, this is r sub k plus delta r over 2, right? It's r sub k plus delta r over 2. Okay? So let's see here. How do I want to do this to make it look the best it can be? So what I want to figure out is what's the area, what's the change in area for this individual polar subrectangle? All right, well, so you have this stuff down here. Right? You have some piece of the wedge, right? Not including this polar subrectangle. And then, how am I going to make this look so it's not going to, so I'm sort of going to try to shade this as lightly as I can here to avoid killing everything. But then you have that piece up there, the polar rectangle in question, right? Well, the change in area, well, what I want to do, I want to take the shaded region and the striped, so this is shaded. This is striped, right? Take the whole area of the whole wedge, and I want to minus off the striped piece, correct? So as silly, it should be striped, as silly as this little equation seems, I mean, area of shaded plus striped minus area of striped will give you area of shaded. That's what I want, right? So to get this rectangle's area, take the area of the whole wedge and minus off this piece down here, okay? So how do I do that? Let's come over here. Well, at least I have an area formula for the wedge. That helps a lot. So delta A sub k, well, what's the area of this whole big piece here, right? Well, it's 1/2 times the radius squared times theta. Well, what's the radius of the whole big piece? This radius right here, right? That's rk plus delta r over 2 squared. And what's the angular measure of the wedge? Delta theta. Okay, delta theta. So that's this guy. That's what that is. Okay, and I want to minus off the stripe piece. Well, the stripe piece has exactly the same angular measure, but a different radius. This radius here, right? So that's minus 1/2 rk minus delta r over 2 squared delta theta. Okay, that's this piece down here. And then let's see here. If you do stuff with this, what do you get? You get 1/2 delta theta times 2 rk delta r. And if you kind of mess around with that a little bit, you get rk delta r delta theta. Okay, that is the expression for delta A sub k. That is the change in area, right? It's the radius of this central point right here times the change in r times the change in theta. And this is important because our whole goal was to get delta A sub k in terms of delta r delta theta, which we've done. So therefore, our sum, right, from k equals 1 to n of f of rk theta k delta A sub k, we can rewrite that sum as the sum from k equals 1 to n of the same junk, right? Only now we've got rk delta r delta theta. And everything's in terms of r and theta, right? Okay. So when I pass to the limit as n goes to infinity of Sn is the double integral over the polar subrectangle, right? Or the polar rectangle r, not the polar subrectangle, f of r theta, r dr d theta, right? And I want to emphasize 2 points. Number one, this is a zooming in on one single polar subrectangle in that big region R. So this looks a lot like R does, but it's a zooming in on one single subrectangle, right? It's a zooming in there, okay? And this is just the rest. In other words, the rest of R is not shown, okay? And this extra R piece out here, that means there's an extra multiple of R in this double integral, Okay, that's crucial. Okay, that's going to help out a lot in a lot of places, especially in terms of doing substitutions. Okay, so let's get rid of this. We're almost to the point where we can start using this stuff. All right, so we're through all the theory more or less. And so remember, our big region R was that big polar rectangle where A was less than R was less than or equal to B, and theta was less than, alpha was less than theta was less than or equal to beta, right? So there's our limits of our polar rectangle R, right? So this expression over here, this double integral, we can do it in terms of doing R first and then theta. So our limits of integration for theta are alpha and beta. Our limits of integration for R are A and B. And we have that R dr d theta, right? And so that's just how we're going to go ahead and use these polar coordinates in doing multiple integrals, okay? All right, so let's do an example and get off of all the theoretical stuff here for a minute. But you see, the important thing was, hadn't we not done all that, we would have never noticed this R down here. We might have just passed the limit and not seen that, and we would have had the wrong answer. So that was important. Okay, so, but now what's important to us is using this formula down here. Okay. So, what have we got? Let's evaluate the double integral over R of x squared plus y squared dy dx. And let's let R be the region bounded by the unit circle and the positive axes. So I want the section of the unit circle in quadrant 1, essentially. Okay, so let's draw a picture as we always do with these problems. That's not a great circle, but it works. All right, so there's my region R. There's one, and out here is the circle x squared plus y squared equals 1. Okay. So we can consider this, let's use the green here, as a type 1 region. Okay. Certainly a type 1 region, right? So our x is bounded between 0 and 1, right? Our y is bounded between y and, let's see here, so if we solve that out, we get y squared equals 1 minus x squared. So y is the root of 1 minus x squared, right? And this is, of course, normally plus or minus, but we're working only in quad 1 here, so just plus. Okay. So there's our limits of integration. So our double integral would look like 0 square root of 1 minus x squared plus y squared dy dx. So there's the double integral that we want. Now, what's going to happen is if we do this in rectangular coordinates, it'll get nasty. It's doable, I think, but to avoid all that, let's use polar coordinates. So how do we convert to polar coordinates? Well, we have the relationships that allow us to do such. So we know that x is our cosine theta. We know that y is our sine theta. And we know that r squared is equal to x squared plus y squared, right? We have those relationships there. And so as a consequence, the inside integral, so we'll leave the limits of integration blank for the time being, well, inside becomes r squared, which is great, right? So inside we just have an r squared, and we can't forget the extra r, right? So the extra r is always there. The extra r is always there in these integrals, right? Dr d theta. What are the limits of integration? Well, think about this. So what are the limits? So how is r entering and exiting here? So our radius here is between 0 and 1, right? This is the unit circle. So certainly you can't have any less the radius of 0, and your radius can't be any farther out than 1 for any point on this sector, right? Because every single point on the circle here is going to give you radius 1. So those are your r limits of integration. And for your theta limits of integration, you're talking about theta being bounded between the x-axis and the y-axis. That's 0 to pi over 2, right? So the theta limits go out here in the outer integral, and the r limits go in here in the inner integral. And now that's the same integral in polar coordinates, okay? So if I go ahead and do that, I get 0 pi over 2. So this is r cubed dr. So that's 1/4 r to the 4th, r equals 0 to r equals 1 d theta. All right, and actually I'm out of room here. Let me come up here and continue this. Okay, so let's see. So that's 1/4 it looks like. So we have integral 0 to pi over 2 of 1/4 d theta. All right. Okay. So that is 1/4 theta from theta equals 0 to theta equals pi over 2. And that equals 1/8 pi. All right. So there's your answer. And honestly, I mean, the conversion made this dramatically easier. It would have been had we tried to plug this function in here and fooled around with it then and done that kind of stuff. So this is much easier. Okay? And the limits are pretty easy to get to. Okay, let's try another one here. So let's look at another circular region. And again, this is, this is not going to work for regions that are going to be significantly funky looking, but if you have circular regions or semicircular regions or things like that, usually this is a pretty good hint that you're trying to use polar coordinates on it. Or at least it might make things a little easier for you. So let's evaluate integral, double integral over r, e to the x squared plus y squared, dy dx, where r is the left half of the circle x squared plus y squared equals 1. Okay. Alrighty, so let's draw our region. All right, so there's +1, there's -1, there's +1. Inside that left half, that's our region R. Okay. So what are the r and theta limits of integration here? The r limits, again, are going to be, let's see, that's actually -1, isn't it? Are again going to be 0 to 1. Remember, r is a radius, so r can't be negative, but it will be 0 to 1 there. And let's see here. The theta limits of integration are going to be from pi over 2 to 3 pi over 2, right? So pi over 2 to 3 pi over 2. Oops, got my theta in there, didn't I? So it should be a theta, 3 pi over 2, like that, right? And this integral, well, again, x squared plus y squared is equal to r squared, so the integral transfers over quite readily. So we can go right to polar here. There's the theta limits of integration. There's the r limits of integration. The function is e to the r squared, r dr d theta. Okay? R dr d theta. Okay? And let's see here. What do I want to do now? Substitute? Yeah, probably. So we'll use substitution. Let u equal r squared. Du is 2r dr. 1/2 du equals r dr. So see how this r helps out here? Otherwise, we couldn't do this, right? So this becomes integral pi over 2 to 3 pi over 2, 0 to 1 of e to the u, and I guess it should really be a 1/2. What did I put the 1/2? Do I put it? Yeah, I guess I put it inside, don't I? All right. So 1/2 du d theta. All right. So there's our substitution. Right. Let's keep going down the board here like this. So pi over 2, 3 pi over 2. So 1/2, and then e to the u from, I guess I can make it back to r squared now. So e to the r squared, r equals 0, r equals 1 d theta. Okay. So I just sub back in. And notice, too, my limits of integration are not changing here with the substitution because these are just 0 and 1, and they stay the same when we're just squaring r. So that sort of works out nicely. So what does this end up being here? Integral from pi over 2 to 3 pi over 2. Let's see here. So we have a 1/2 hanging around. E to the r to the 1 is e, and e to the 0 is 1. So that's a minus 1/2 in terms of d theta. All right. Okay. Let's come over here maybe and keep working. Get rid of substitution. So now we'll keep going over here. So let's see, this ends up being what, 1/2 e theta minus 1/2 theta, theta ranging from pi over 2 to 3 pi over 2. Is that what I have here and everything? Yeah, looks good. And let's see, plug that stuff in. You plug in 3 pi over 2. You get what? 3 pi e over 4 minus what? 3 pi over 4. And then let's see here. So then you've got what? Pi e over 4. You got a minus pi e over 4 and a minus. Oh, actually, that would be a plus pi over 4, wouldn't it? Yes, it would be. Okay. So let's see here. Let's see. So 3 pi minus pi is a 2 pi over 4 times e, which is what? Pi over 2e, and then minus pi over 2, right? When you can write that as what? Pi over 2 times e minus 1. Is that what I've got? Yeah, looks good. Okay, so there's your integral. And in that case, the r really saved us down here. It allowed us to do the substitution. But that wasn't too bad with polar coordinates. Pretty straightforward. Okay. So area. Let's do an area problem here. Let's get rid of all this. So remember, we talked about area in the last lecture. Area of a plane region in rectangular coordinates remember that was double integral over r of 1, what do I have here, dy dx. Yeah, so dy dx. And so the same kind of thing applies for polar integrals. Area of a plane region in polar coordinates is double integral over r. Remember, the extra factor of r is hanging around there, so it has to be r dr d theta. Okay? So let's try this formula out on a problem. So get rid of that. Okay. So let's find the area of the region within the circle R equals cosine theta. Okay. Okay, well, first of all, what does this thing look like? All right. It's given in terms of polar coordinates. We have to kind of figure out what's going on with this here. So let's see here. So if x equals r cosine theta, then r is equal to cosine theta here. So that's r squared, right? And r squared is equal to x squared plus y squared. So the conclusion I'm drawing here, after doing that little substitution, is that x is equal to x squared plus y squared, right? Okay. So we're going to move things around a little bit. We have x squared minus x plus y squared equals 0, right? I'm going to complete the square on this. So I take half of this and I square it, and I add and subtract that to both sides, right? So I get x squared minus x. Half of -1 is a -1/2. If I square that, I have a plus 1/4, right? And I have to also minus a 1/4 from both sides. So I'll do that. So I guess I'll put it like this. And then we can't forget the y squared either. So plus y squared equals 0. So this condenses to x minus 1/2 squared, right? That's our perfect square trinomial. This plus y squared hangs around, and the 1/4 gets tossed onto that side, right? And so what does this actually look like? Well, it's a circle. Well, it has center 1/2, 0, and this is r squared, so the radius is 1/2. Radius 1/2, right? So this is a circle with center 1/2, 0, and a radius of 1/2, right? So that was a little bit of maybe not ingenuity there, but just sort of looking at what I had here and getting into something nice. So I can draw my region now. So there's 1 out there. There's a 1/2. So there's a 1/2, and there's 1. So let's see here. And then put a 1/2 down there and 1. So it doesn't look very circular, is it? Well, let me just draw the circle, then I'll put the hash marks on there. So, well, not a great looking circle, but it's all right. So now there's 1, and there is, that's a 1/2, and that's a -1/2, and that's 1, and that's a 1/2 there. Okay, so yeah, so there's your circle. So your theta limits of integration, you're asking yourself, well, what kind of thetas can I put into this? Well, r can't be negative, so the cosine of theta is bigger than or equal to 0 in quads 1 and quads 4. So your theta limits of integration are -π/2 to π/2, right? And what are your r limits of integration? Well, again, I mean, if theta is π/2 or -π/2, r is 0. That certainly bounds it. And everywhere else, it's bounded by the function cosine theta, right? So there's your r limits of integration, okay? So once we've gotten all that out of the way, we have our appropriate limits. So what we want -π/2 to π/2. We want 0 to cosine theta. And notice this is just like any other integral. Our first limits of integration depend on theta, and then after that we'll have only constant limits of integration. And then we have r dr d theta, right? Okay. So let's crank this out here. So -π/2 to π/2. And we have 1/2 r squared evaluated from r equals 0 to r equals cosine theta, d theta, all right? Okay, so that means we have the integral of negative pi over 2 to pi over 2. The 0 cancels. So we get what? Cosine squared theta over 2. Is that right? Yeah. Okay. And that in terms of d theta. And so now what do I do? Do I do a trick here? What happened to... Oh, yeah, I see what happened here. Okay. Yeah, so here, well, it's those darn trig identities you got to kind of keep in the back of your mind here. So, not what you're going to do with this probably, but you can certainly probably find an identity that deals with it, and you can. This is a half-angle formula. So by half-angle formulas, this ends up being what? Ends up being 1/2 times 1 plus cosine 2 theta over 2. And actually, I guess I wrote this in a different way, so let me alter this up here slightly. So just to make that very clear here, I wrote this as 1/2 times cosine squared theta d theta. So I'm actually just leaving the 1/2 alone, and I'm looking at the identity here only on the cosine squared, right? It's this thing down here, right? That's the half-angle formula. So it's half-angle formula. Half-angle formula. And again, that's kind of how it goes with these problems. If you're sort of stuck integrating somewhere, probably there's a formula out there that's going to help you out. So take a look around in your old pre-calc book or something like that, and you'll probably find a formula that's pretty good, or look on the internet, and it probably has some pretty good formulas there to take a look at. Okay? So this is much more easily able to be dealt with. So let's see here. What am I going to do? Oh, yeah. Well, I can pull these 1/2 out of there, so I can get a 1/4 on the outside, and then I'm only left dealing with, what, 1 plus cosine 2 theta d theta, right? And so where do I want to come now? Maybe over here, right? And so let's see. So I've got 1/4, and integrate that with respect to theta. You get theta plus, so you got cosine 2 theta here. So let's see. So it came from what, 1/2 sine 2 theta? Is that right? All right. So does that look good? 1/2 sine 2 theta? Yeah, it looks good. So sort of reversing the chain rule in our head here and doing 1/2 sine 2 theta, right? And so our theta angles are negative pi over 2 to pi over 2, right? And let's see here. So when you crank that out, what do you get? You get 1/4 times pi over 2 plus, let's see, so sine of 2 times pi over 2 is a sine of pi, which is 0, so that goes away. And then we get a minus negative pi over 2. And when I plug in a negative pi over 2, you get sine of negative pi, which is also 0. So this works out nicely for us. So we get 1/4 times pi. And so is that right? Pi over 2 plus pi over 2? Yeah, that's pi. So pi over 4. Right? So there's the area. Right? Yeah, that's what I got. All right. And so that concludes the section on double integrals in polar coordinates.